Okay, let's just jump right into this. We are looking at the genuinely fascinating science of how human beings will actually survive a mission to Mars. Now, we've been sending robotic emissaries to the Red Planet for decades, right? They gather data, they map the surface, they snap those totally spectacular photographs we all love. But putting actual human boots on Martian soil, that presents an entirely different set of challenges. Because it's not just about surviving the journey there, it's about staying alive once you arrive, and then ultimately finding a way to blast off the surface and actually come back home. Now, the absolute biggest, most immediate logistical nightmare of space travel is weight. Every single ounce of material you strap to a rocket requires exponential amounts of fuel just to escape Earth's gravity. So think about this. How exactly do you pack enough heavy rocket fuel and breathable air for a multi-year trip to another planet? Spoiler alert, if we try to bring absolutely everything with us from Earth, every single breath of oxygen, every drop of water, and literally tons of methane propellant for the return trip, the mass of the spacecraft becomes so astronomically huge that the entire mission becomes practically and financially impossible. So the simple, kind of mind-bending answer to this massive logistical hurdle? You just don't pack it at all. You make it when you get there. Instead of treating Mars like some desolate campsite where you have to haul in all your own provisions in a backpack, we have to start treating it like a frontier where we can actually synthesize what we need directly from the alien environment around us. And that brings us to the absolutely crucial concept at the heart of this explainer, ISRU. That stands for In Situ Resource Utilization. Basically, think of it as the ultimate ultra-high-tech version of living off the land. Just like early pioneers learned to harvest local timber to build shelter or use local water for farming, our future astronauts are going to use advanced chemical processing to harvest the Martian atmosphere and soil. So this isn't just some neat parlor trick. ISRU is literally the fundamental enabling technology for sustainable, affordable human exploration of the solar system. But to figure out how to actually live off the land, we first have to know what resources we have to work with. And for that, we can look all the way back to measurements from the Viking landers. The air on Mars is overwhelmingly carbon dioxide. We're talking over 95%. There are traces of nitrogen, argon, and this tiny, almost negligible fraction of oxygen. Now, to human lungs, breathing that atmosphere is completely useless. But to a chemical engineer, that 95% carbon dioxide is an absolute goldmine. It's just a massive reservoir of carbon and oxygen atoms waiting to be pulled apart and recombined. Now let's talk about the fuel requirements for a second. If we want to launch a rocket back off the surface of Mars to bring our astronauts home, we're going to use a liquid oxygen and methane engine. But here is the tricky part. We need an oxidizer to fuel mass ratio of about 3.4 to 1. What does that mean? It means for every single pound of methane fuel we burn, we need almost 3.5 pounds of pure oxygen just to combust it. So bottom line, we need way more oxygen than we do methane. So how do we solve this? Well, we use an incredibly clever chemical process known as the Sabatier process, or methanation. This is our primary method for making that much needed rocket fuel literally out of thin Martian air. Now, this is actually a well-known chemical process used in industry right here on Earth, but adapting it for the harsh, unforgiving environment of Mars, that requires some serious engineering magic. Gases have to flow through heat exchangers into a catalytic reactor and then into condensers just to separate out those valuable liquids. But what's actually remarkable is that we can break that intimidating chemical engineering down into 4 surprisingly straightforward steps that basically turn thin air into explosive rocket fuel and water. Step 1, we capture that abundant carbon dioxide straight from the Martian air. Step 2, we combine it with a small amount of hydrogen. Step 3, we run that mixture through a highly heated reactor filled with a catalyst, usually something like nickel or ruthenium. And finally, step 4, the chemical reaction outputs methane, which is our rocket fuel, and liquid water. From there, we can literally crack that water apart using electricity to get our breathing oxygen and recycle the leftover hydrogen right back into the start of the loop. Pretty amazing, right? But, hey, remember that 3.4 to 1 ratio we just talked about? Yeah, the Sabatier process alone doesn't actually give us quite enough oxygen to burn all the methane it produces. So, to get that massive amount of supplemental oxygen, engineers proposed a companion system called the Reverse Water Gas Shift, or RWGS process. By running Martian carbon dioxide and hydrogen through this specific reactor, we produce carbon monoxide, which we just discard, and water. Then, we heavily electrolyze that water. This system gives us an incredibly high leverage on producing liquid oxygen. And that's crucial, not just for rocket propellant, but for guaranteeing a reliable supply of breathable air for the crew habitat.
Of course, actually building the reactors to execute these chemical processes on Mars, that forces us into some pretty tough engineering dilemmas. We basically have to choose between traditional packed bed reactors or highly efficient microchannel reactors. Packed bed reactors are your old reliable standard, but they're heavy, and they can develop these localized hotspots that totally ruin the catalyst. Microchannel reactors, on the other hand, deposit the catalyst directly onto the microscopic walls of the reactor itself. They offer massive weight savings and incredibly precise temperature control. But they are extremely delicate. If even a single trace impurity or a microscopic speck of sulfur-rich Martian dust slips into that gas stream, it can instantly deactivate the catalyst and completely shut down your only fuel factory. No pressure, right?
Now, before we can even run those reactors, we need a way to actually capture and compress the Martian carbon dioxide. Keep in mind, the atmosphere there is incredibly thin, about 100 times thinner than Earth's. Trying to compress it mechanically would require heavy, power-hungry pumps that would almost certainly just get clogged with Martian dust. Instead, researchers figured out that freezing the CO2 directly out of the atmosphere, literally cryo-freezing it into dry ice, is far and away the smartest method. It requires significantly less power, it naturally purifies the CO2 by just leaving the trace gases behind, and the best part? When you warm that dry ice up in a sealed tank, it automatically generates a high-pressure gas feed for your reactors. It saves huge amounts of mass and energy. And this is where we see the incredible leap from mere theory to actual reality. We've gone from the 3D CAD designs of CO2 freezer modules, systems using cryocoolers, chilling copper down to a staggering 150 Kelvin, to actually creating it. NASA literally pulled carbon dioxide out of a vacuum, simulating the low-pressure Martian atmosphere in a lab, and froze it solid into actual dry ice. It absolutely proves that the atmospheric capture phase of ISRU works beautifully. So the freezing experiments and Sabatier reactors are tested and perfected here in Earthbound laboratories. But we all know the ultimate test is doing it on the actual planet, dealing with the real abrasive dust, the severe temperature swings, and the intense radiation. So to prove this wasn't just a wakeboard theory, NASA sent a microwave-sized device called MOXIE to the Red Planet. It hitched a ride aboard the Perseverance rover back in 2021 with one mission: to prove once and for all that we could make our own oxygen in real time, in a real Martian environment. And over the course of the Perseverance mission, MOXIE didn't just work once. It was a repeated, undeniable success. This amazing little instrument successfully separated oxygen atoms from Martian carbon dioxide 16 different times. It operated under a whole variety of harsh seasonal conditions throughout a full Mars year. In total, this demonstration unit generated 122 grams of breathable oxygen. Now, to ground that number in reality for a second, 122 grams might not sound like enough to fuel a giant rocket ship just yet, but it is exactly what a small dog breathes in about 10 hours. And look, the true victory here wasn't the total volume, it was the precedent. This was a monumental first step for extraterrestrial manufacturing. It's literally the very first time humanity has ever processed the natural resources of another planet to create a consumable product that we can actually use to survive. That is huge. And honestly, even more impressive than the quantity was the exceptional quality of the product. At its peak efficiency, churning out about 12 grams an hour, which, by the way, exceeded NASA's original design goals, MOXIE was producing oxygen at an astounding 98% purity, or even better. And whether you're pumping it into an astronaut spacesuit to breathe or mixing it with methane to ignite a rocket thruster, you absolutely need extreme purity. MOXIE proved, without a doubt, that extracting high-grade oxygen from the toxic Martian air is completely viable. Trudy Cortez, the director of technology demonstrations at NASA headquarters, really hit the nail on the head. She said that by proving this technology in real-world conditions, we've come one step closer to a future in which astronauts live off the land on the Red Planet. This wildly successful experiment proves that ISRU isn't just science fiction anymore. We actually have the definitive roadmap for a sustained, economically viable human presence on another world. So, wrap your head around this. We've officially proven we can freeze the atmosphere, process it through chemical reactors, and make our own breathable air and our own rocket fuel out of the harsh Martian environment. We have the technology to live off the land, which is going to dramatically reduce the weight and the cost of future spacecraft. And really, that leaves us with just one lingering, provocative question as we look up at the night sky. Now that we know exactly how to pack for the trip, when do we leave?